So this video is a continuation of and a dive into the discussion from the previous video, the chapter 6 from Language, Proof, and Logic overview video, where we talked about the derivation rules for negation, conjunction, and disjunction in a just a rather introductory way. Here, what I want to do is take a deeper dive into the ways in which you can understand what these rules mean and how to use them. And then in a separate video, I will take time to work through a good number of examples of using the negation, conjunction, and disjunction rules, more specifically examples of how you can use the negation intro and disjunction elimination rules as structuring rules for a proof. So our goal is going to be ultimately to develop a set of strategies that is really hone your strategic thinking skill set, so that when you're looking at an argument, even though it may be the case that you don't see in detail every move you're going to make to prove the conclusion, you'll at least have a picture, a big picture of the strategy that will get you to where you want to go. And then once you set up that strategy, you'll start to see the sub-strategies and tactics lay out. Okay, so let's go in order of the presentation way back in chapter 3 for the truth definitions of respectively negation, conjunction, and disjunction. In between, we will talk about the concept of a logical contradiction, more specifically a truth-functional contradiction, as contradiction plays a very important role in our negation intro derivation rule. So as a reminder, the definition, the truth definitions for the negation are as follows. When some sentence P is true, the negation of that sentence is false. When some sentence P is false, the negation of that the negation of that sentence is true. So let's bear in mind as we go forward this fact about what the truth functional definitions are. So let's focus on an important feature of the truth definitions of the negation. The values of the negation contradict the statement negated. So when P is true, not P is false. When P is false, not P is true. So let's bring that notion of contradictory truth values to the fore as we look at the argument that is listed on or shown on the right side of your screen to the right of the text. Let me go ahead and grab the pen. We've got two premises and a conclusion, and we have the argument laid out as we would see in a truth table. What I'm going to do, however, rather than construct a completed truth table, I'm going to combine two concepts that we already understand. One, the concept of contradictory truth values, and two, the concept of a valid argument. Now, we know that an argument is valid when it's impossible for the conclusion to be false if the premises are true, or when the premises are true. So what if, knowing that this argument is valid, this argument is P or Q, not P, so Q. It is the dismantling, the conclusion rather, is the result of dismantling the disjunction. When we say we have P or Q, we say we have at least one or the other. And if we deny we have the one, namely if we deny we have P, we're left with Q. But what if we say that the argument is invalid? In other words, what if we say that the conclusion is false and the premises are true? Now, when we have a valid argument, we will see by the definitions of our connectives that it is impossible to maintain invalidity. In other words, saying that the argument is invalid will generate a contradiction at the level of the truth definitions. So how does this play out? Well, let's take a look. If we say that the conclusion is false, we go ahead and plug that value under Q. And we know that if we're saying the disjunction is true while Q is false, while one of the disjuncts is false, then in order to preserve this truth value, P has to be true. But look at what happens. If we say that P is true, but not P is also true, we've generated a truth functional contradiction. P can't be true while not P is true, and vice versa. Let's try this again. In other words, let us once again assume the conclusion is false while the premises are true. This time, let's work from the second premise, which we're saying is true. That makes P false. We plug that value under the corresponding atomic sentence in the first premise. And then we go to the conclusion, which we've assumed is false. We plug that in, again, under its corresponding premise. And here again, we've got a contradiction. In other words, we've assumed that the disjunction is true, but it can't be true if each of the disjuncts is false. So what the indirect truth table shows us is when we have a valid argument, but we assume that the argument is instead invalid, we run into a contradiction at the level of the truth definitions for the relevant connectives. And this notion of contradictory values is what's at the heart of negation introduction. This is a rule, also known as indirect proof. It is also a reductio ad absurdum, or reduction to a logical contradiction. The strategy being a version of what we just did with the indirect truth table, namely assuming your conclusion is false. So that is assuming the opposite of the conclusion as a true sentence. From that assumption, deriving a contradiction, and then asserting outside of that assumptive proof the fact that that assumption is not true, which is to say, introducing the negation. So yes, it is, it might feel, or it is, counterintuitive at first, just like maybe the indirect truth table feels counterintuitive. But as you go forward, you're going to find that it is a really powerful tool for generating the conclusion that you want. So the general strategy is this. When you're given your argument, you look at the conclusion, you see that the conclusion is an atomic sentence or a literal, that is a negated atomic sentence. You assume that the conclusion is false. In other words, you take the opposite of the conclusion and accept that as true. So you start a subproof. From that assumption, you generate a contradiction, which then tells you it's time to get out of that subproof and introduce the negation, which is to say, when you introduce the negation, you're effectively saying that that assumption you made is not the case. So again, it's a really powerful strategic tool, and we'll find that we can use it for any valid argument, but the general strategy is what I just mentioned, namely you take a negated sentence or an atomic sentence or a negated atomic sentence, which is a literal, and you assume that the opposite of that sentence is the case. From that, you generate the contradiction, get out of the subproof. So here's an example with which you're already familiar. You have the following structure, and then I've given you an example. So the structure is this: if P, then Q, not Q, so not P. Here's the example. If I have 10 pennies, then I have 10 cents. It's not the case that I have 10 cents. Therefore, it's not the case that I have 10 pennies. Notice that the two sentences in red are contradictories, and the contradictories generate a contradiction of, in this case, the hypothesis that I have 10 pennies. Now, in some versions of the deductive system that we learn in a course like this, you're given this inference as a rule form. So whenever you see an if-then sentence and a negation of the then, in other words, when you see a conditional claim and a negation of the consequent, you can infer the negation of the antecedent. In our version of the system, we don't just use this rule, we actually prove the rule. So what we do is this. Okay, so here you have in Fitch format the argument that you just saw in ordinary language. Now, I recognize that this arrow symbol is not one with which you are officially familiar as yet, but it's pretty intuitive, I think, to say that it represents what we've just said, the if-then claim. Now, in subsequent videos, we'll talk about the truth definitions for this symbol, and we'll talk about the inference rules that involve it. But for right now, the focus here is on demonstrating the claim I made just a moment ago, namely that when we have the denial of the consequent, so the consequent is Q in line 1, and the denial of it appears in line 2, those are the premises we're given, we then achieve, which I'm highlighting in green, we then achieve the denial of the antecedent. So indirect proof, aka reductio ad absurdum, known in our version of the system as negation intro, works this way. We assume, which you set up in Fitch with either Command P or Apple P, or if you're in a Windows-based system, Control P. That starts off an assumptive proof. If you want to use the drop-down menu, you will go under the proof drop-down menu, and you'll see new subproof, and that's what you want to click. All right, so what do we do? As I mentioned, we assume that our conclusion is false, which is to say, we assume instead that P is true. And the idea is to generate a contradiction. I'm hitting the contradiction button in the button menu, so that we can say that this assumption yields a contradiction from which we can then infer that that assumption is false, which is to say we can introduce the negation. Now, we won't have the rule for the following inference, but for right now, I'm just going to say when we infer Q that is going to be a tautological consequence, right? That is a truth functional consequence of lines 1 and 3. Now, the contradiction between 2 and 4 is inferred at line 5, and the truth definitional contradiction symbol is justified by the contradiction intro rule. So we can say, therefore, click anywhere in your subproof and the whole subproof highlights, when we've achieved the contradiction, it follows that this assumption at line 3 is not the case. Remember, if we go back into our truth table, we can see that when you generate a truth functional contradiction in the case of a valid arguments being assumed, the valid argument's conclusion being assumed false, that if in fact the conclusion is false, there has to be at least one false premise in the truth table. And so what we're saying is that we can't have not Q and Q at the same time. So one of the premises must be false. That is, either line 1 must be false or line 2 must be false. And that's because the conclusion, in this case not P, must be true. All right, so I'm going to assert that the negation introduction rule justifies line 6, and the citations, that is the sources of my justification, are 3, 4, and 5, but I cite them collectively as the subproof. And now I'm going to verify the proof, and I get check marks. All right, this is a tough rule to learn, but as you get the hang of it, it will become easier and easier. As with all things, the more you practice, the better things get. I will have a video, more than one video, devoted to practicing with our inference rules from chapter 6, as well as later on chapter 8. Here you see a summary of what we've just discussed. On the right side of your screen, to the right of the text, you'll see the negation intro rule form. Notice that the presentation that I've offered is a little less visually complicated than what you see in the text, but that's just, again, to give you as clean a presentation of the rule form as possible. So what you'll see is a set of vertical lines. The first vertical line is the proof sequence from which you indent or inaugurate the assumptive proof. So the indented sequence, where you see P as an assumption, is what sets off the negation intro rule. From the assumption P, you generate a contradiction, then you exit the subproof, and you assert that that assumption P is not the case. That is, you introduce the negation. Now you see the contradiction symbol. I've already discussed it a bit, but now let me say a bit more about that contradiction symbol in connection not only with truth functional contradictions, which is when you enlist the rule contradiction intro, but also our broader notion of a contradiction. So we're given the rule contradiction intro, which we use to justify a truth functional contradiction, namely P and not P. When we have another type of contradiction in our version of the system, when we have what's known as an analytical contradiction, that is a contradiction based on the meanings of the terms that we're using, then we can use the contradiction symbol, but we do not use as a justification the contradiction intro rule. Instead, we use the symbol, but we justify the move that we've made, that is the contradiction assertion, by way of anacon. And that's just a way for our Fitch program to know that, yes, we've generated a contradiction, but it's not of a truth functional variety. So think about, for example, the fact that we know, based on the meanings of large and small, that A can't be both large and small. Notice if we assert A is large and somewhere else in our proof we assert A is small, we've asserted we've two contradictory claims, but there's no negation symbol. It's not a truth functional contradiction. So we do not justify the assertion of the contradiction according to contradiction intro. Instead, we assert it according to the anacon justification. So we'll see more of this when we get to some practice together. Meanwhile, take a look at the rule before moving on. So we can introduce a truth functional contradiction. We can also eliminate a truth functional contradiction. Now, this may be a little bit difficult to understand at first. It may feel like an arbitrary rule, like we're cheating somehow, right? But the short story with the contradiction elimination rule is this. Once a contradiction has been generated, anything follows. More specifically, in our version of the system, once we've generated a contradiction, there are two possible moves. You either end a subproof that you're in, exit that subproof, and assert negation intro, or immediately after the contradiction symbol, within the same line of the sequence you're in, whether it's a subproof or not, you assert whatever sentence you want, and the sentence you want is typically a sentence that either concludes the proof or that gets you another step closer to concluding the proof. So let me address the natural question that arises, which is, wait a minute, what do you mean from a contradiction anything follows? That feels like I'm cheating, or that feels like, just like I'm flouting some, rule of the universe. No, you're not. You're neither cheating nor flouting a rule of the universe. Let me try to explain it this way. We know that denying the conclusion of a valid argument is absurd. In other words, denying the conclusion of a valid argument generates a contradiction in one or more of the premises. We also know that we can prove the denial of the valid argument's conclusion is untenable by assuming that conclusion is false. So let's think about that as we move on to, say, the following. Let's suppose that a contradictory sentence is true. In other words, let's suppose that the sentence, Larry the parrot is and is not speaking, is true. We know that a true conjunction means each of the conjuncts is true. That would mean, therefore, that P is true and not P is true. Since P is true, it follows by a rule that we will learn in just a moment, but that we already know by definition is true, namely that Larry the parrot is speaking, or anything I want to say is true. Q, Santa Claus is real. So either Larry the parrot is speaking or Santa Claus is real is true. We also know that since not P is true from the conjunction P and not P, it follows that Q is true. In other words, if it's true that Larry the parrot is speaking or Santa Claus is real is true, and we also know that the sentence Larry the parrot is speaking is false, in other words, it's not the case that Larry the parrot is speaking, it follows that Santa Claus is real. So, from a contradiction, namely P and not P, anything Q, in this case Santa Claus is real, follows. One of the things that I want you to think about, though, is this. If you feel like you've just gone through an intellectual version of Twister, in other words, if you feel like you're playing mental Twister right now, don't fear. Just know that when you generate a contradiction, if you're in a subproof, you've set up negation introduction, you exit the subproof, you assert the introduction of the negation. Alternatively, once you generate a contradiction, you stay in the sequence you're in, whether it's a subproof or not, and you assert the desired sentence. So from a contradiction, anything follows. Here's what the rule looks like. When you generate a contradiction, you stay in the same sequence where the contradiction is asserted, and you assert after that contradiction P, whatever that sentence is. It's going to be a sentence that either concludes the proof, or it's going to be a sentence that gets you closer to that conclusion. All right, so we've spent a lot of time on our first rule and two related rules, namely, we've spent a lot of time on negation introduction, and then we talked about contradiction introduction and contradiction elimination. Now let's talk about the parallel rule, the symmetrical rule for negation intro, and that is negation elimination. It's a pretty straightforward rule. From two negations, you assert the affirmative. In other words, we know that truth functionally, a double negated sentence is equivalent, truth functionally, to the sentence P. So negation, negation P, or double negation P is truth functionally equivalent to P. So we don't see this rule come up too often, but it's a good rule to have when it does come up. We want to employ it. When the opportunity to use it comes up, we want to employ it. All right, moving on to conjunction. The intro and elim rules for conjunction I think of as tactical rules. That's because the rules for conjunction do not require any subproofs. As a reminder, we know that the conjunction is true when and only when each of the conjuncts is true. So, if you want to create a conjunction, you have P and Q somewhere in your proof, you can assert the sentence P and Q. You can also look at the right side. The second version of the rule is this. If you have P and somewhere else you have Q, you can assert Q and P. So notice that, let me just grab the pen to make this clear. This is the alternate, right? So there are two at least moves that you can make here. You can have from P and somewhere else in your proof Q, you can say P and Q. Alternatively, if you have P and somewhere else in your proof Q, you can say Q and P. Similarly, if you have Q and somewhere else in your proof P, you can have P and Q, and you get the idea, right? That's why I mentioned that I've given you an alternative, but there are more alternatives. In other words, any two sentences that are on two separate lines of a sequence can be conjoined, justified by the rule conjunction intro. So here's an example. The moon is an astronomical body and the sun is an astronomical body. We can conjoin those two sentences to conclude, therefore, both the moon and the sun are astronomical bodies. Conjunction elimination also follows our truth functional definitions of the conjunction. Remember, a conjunction is true when and only when each of the conjuncts is true. So, when you have a conjunction, you can eliminate one of the conjuncts. I don't think this rule needs a whole lot more explanation. If you want to pause and take a look at the examples that I've offered, go for it, and then resume when you're ready. And again, we'll get some practice in another video. Next, let's review our definitions for the disjunction. We know that a disjunction is true in three ways, right? A disjunction is true when at least one of the disjuncts is true, and in fact can be true, or is true, I should say, when both disjuncts are true. So now let's suppose that you want to create a disjunction. You know that all you need for a disjunction to be true is at least one of the disjuncts to be true. So if P is true, P or whatever you want to say is true. When P is true, P or Q is true. And sorry, this is a typo, but rather than go back and fix it, I'm just going to write over this Q. When Q is true, P or Q is true. So again, there are variations on this rule, but what you're getting when you have P and when you have Q is are two versions. In other words, any sentence in the universe that is on a line in your proof can be expanded by way of disjunction intro, so that you're saying that sentence or any other sentence is true. The moon orbits Earth, therefore the moon orbits Earth, or the moon is made of green cheese is true. Now, of the rules that we're looking at in this video, 2 involve subproofs, that is, assumptive proofs. We've already seen one, negation intro. Here's the other, disjunction elimination. Now, don't forget, there are 3 ways for a disjunction to be true, right? Pause for a moment if you want and read this slide and then resume play. Now, when we're given a disjunction, or let's say somewhere in our proof we've derived a disjunction and we need to dismantle it, what we want to do is remember the following. Since we don't know which of the 3 ways the disjunction is true, we go ahead and assume the left side of the disjunction, derive the desired conclusion, eliminate or exit, I should say, that subproof, begin a new subproof immediately after, this time assuming the right side of the disjunction is true, derive from that side of the disjunction the same desired conclusion, so that you can get out of that second subproof and assert the following. Whether I have one or the other, I have this sentence S. Now in chapter 5, you get some nice examples of what's known as proof by cases. There are lots of great lots of great examples for proof by cases. Typically what you're doing is saying it doesn't matter which side of the disjunction is true. Maybe both sides are true, but in either case, whether one or the other is true, I get my conclusion, in this case, some sentence S. All right, so you can see that I have an argument laid out in Fitch. Premise 1 says P disjunction Q. Premise 2 says it's not the case that Q. And then our conclusion is Q. That's our goal. So we're going to set up, by way of our newly learned rule, disjunction elimination, we're going to set up disjunction elimination as our structuring subproof. So we do that as follows. We assume P, and our goal is going to be Q. I don't know how many steps that will take, so I add a couple steps after my assumption. Then I exit that subproof and immediately start the next one where the assumption is Q, and I want Q as my goal so that I can exit that subproof and assert that in either case I have the goal Q. Right? So notice what we've done is use disjunction elimination to structure our derivation, and that is basically another way of sort of setting up a roadmap or a blueprint or dots that we then connect on our way to the conclusion. Notice also that the strategy is this: when you set up disjunction elimination, you have as your conclusion for each of the subproofs the conclusion of the argument. Now, this is a general strategy. Sometimes disjunction elimination will have as its goal a different conclusion than the conclusion of the argument, yet it is a conclusion that you need in order to get to the conclusion of the argument. Okay, so what else do we know? We know that not P and P are contradictory. So from 2 and 3, we infer a contradiction. Remember also that from a contradiction, anything follows. So we eliminate that contradiction at 5. So that ends the first disjunction elimination subproof. We move on to the second disjunction elimination subproof. As a reminder, your disjunction elimination subproof involves 2 successive subproofs or 2 successive assumptive proofs, each of which derives from respectively the left and right side of the disjunction the same conclusion, in this case Q. Now we've assumed that we have Q, so we have Q. We're going to reiterate at line 7 our assumption at line 6. Reiteration is simply a rule that tells us that on the assumption that we have some sentence, or when we're given some sentence, it follows that we're saying we have that sentence. Now, from each side of the disjunction at line 1, respectively 3 to 5 and 6 to 7, we have derived our conclusion. Notice that when you cite your lines, you include the disjunction that sets off the elimination. So let's go ahead and verify our proof, and yay, we've got it right. Okay, so we've learned several rules, specifically intro and elim for negation, contradiction, conjunction, and disjunction. Our 2 strategic rules are negation intro and disjunction elimination. My advice to you is the following. Enlist negation intro whenever your conclusion, your argument's conclusion, is an atomic sentence or a literal, that is a negated atomic sentence, but you can use negation intro for any argument, again, assuming the argument's valid, right? So use negation intro when your argument's conclusion is a negated sentence or an atomic sentence or a literal. Use disjunction elimination when in your premises you have a disjunction. Now, there are going to be some variations and there are going to be some flexibility, and there is some flexibility in terms of which strategy you choose when more than one is available. But for right now, just think about like in the Karate Kid doing the Miyagi moves, right? Wax on, wax off. When you see a disjunction in your premises, set up disjunction elimination. When you see a negation or an atomic sentence in your conclusion, set up negation intro. I hope that more than just doing what you're told to do is how you feel right now. In other words, I hope this video helps you to understand why and how we use the rules, not just being given the rules and being told to employ them. But if you're still struggling with your comfort level, then think about doing those Miyagi moves until you've had enough practice to where things start to feel comfortable and it makes sense to you. I hope this video has been helpful to you in increasing your understanding of how we can assemble and disassemble sentences using introduction and elimination rules. There is going to be practice that we can do together. So look for that video if it's not already up. It will be shortly. And I will also see you again when we talk about the last 2 connectives in our version of the deductive system we're learning, namely the conditional and biconditional. That's language proof and logic chapters 6 and 8, the latter for the intro and elim rules for those symbols. All right, if you have questions, as usual, let me know. Otherwise, happy practicing.